Hi! Good day! I'm Krissel C, Bucog, and I'm going to give you a little idea of what diode is all about. Let us define what is a diode. A diode is a two-terminal electronic component with a symmetric conductance. It has low resistance to current flow in one direction. Diodes were the first semiconductor devices that only conducts current in only one direction. Look what I have here. These are some types of special purpose diodes. First, we have the light emitting diode, or the so-called LED. This one is a photodiode, a pin diode, and a Schottky diode. And today, you'll know more about a light emitting diode, or LED, is a semiconductor light source. LEDs are used as indicator lamps in many devices. And to know more about this kind of special purpose diode, let's watch this video.
Have you ever wondered how many of the devices we use on a daily basis operate? The alarm clocks that wake us up in the morning to the streetlights outside of your home all share something in common. This technology is known as a light-emitting diode, also known as the LED. Hi, my name is Kristen C, and I'm here to represent our company called Tech Geeks. It is my pleasure today to walk you through this revolutionary technology that is still evolving to this day. Throughout this video, you will discover why this form of technology in particular exceeds other leading forms of technology of the present day. So who was responsible for the LED? Well, the LED originated from the University of Illinois, where Professor Nick Holonyak Jr. did his research in the General Electric Research Lab. He concluded that LEDs were simply small light bulbs that fit well into an electric circuit. Professor Holonyak had discovered that the LED was a form of a semiconductor, which is a material able to conduct electricity under certain conditions. The conductor material in the LED in particular is named aluminum gallium arsenide. Entirely pure forms of this conductor cannot induce electricity because there is a perfect bondage between the contained atoms and their surrounding atoms, which leaves no free electrons to produce current. We can alter the conductor in order for it to actually conduct current through a process called doping. In this process, additional free electrons are added to the conductor to make the material more conductive. We can witness this phenomenon through many technologies one uses daily, like in our computers, cell phones, digital clocks, downlights in a kitchen, calculators, flashlights, holiday lights, and many more. It is evident that the light-emitting diode has been utilized for many successful and what we consider necessary products one needs to live. It's quite interesting in knowing how a light-emitting diode functions. A diode can be defined by an electrical component with two terminals that allow electricity to flow in one direction only. As mentioned beforehand, LEDs function by moving electrons through a doped semiconductor. Doping allows extra electrons to move from a negatively charged area to a positively charged area. LEDs contain specific semiconductors that can either be called N-type material, where the charged carriers are electrons, or P-type material, where the charge carriers are made up from the absence of electrons, or holes. An LED is composed of these two types of materials bonded together, called a junction. This allows for additional electrons to jump from positive hole to positive hole. Consequently, the holes appear to become negatively charged, and there is a creation of an insulation layer in the middle of the diode called a depletion zone. The depletion zone is home to a space where all positive holes are filled, and no free electrons are able to fill the spaces, and therefore no current can flow. In order to return to a state where current can flow, the N-type of the diode must be connected to the negative terminal of the circuit, as well as the P-type side of the diode to a positive terminal of the circuit. The electrons moving freely in the N-type material are as a result repelled by the negative side of the circuit and attracted to the positive terminal. Meanwhile, the holes in the P-type material are attracted to the negative terminal of the circuit. Electric charge is able to move along a path when there is enough potential difference or voltage between two terminals. When this does happen, the electrons contained within the depletion zone are pushed out of their holes and begin to move freely once again. Amazingly enough, when there is enough power added to LEDs, it excites the electrons leading to the production of light. LEDs come in a variety of colors depending on the type of semiconductors present. Now that we're familiar with how an LED functions, let us discuss the advantages an LED has over any other light-producing technologies. While LEDs are more costly than a regular light bulb directly, their benefits in the long run make them a much better purchase. One might also be unwilling to buy an LED because of the fact that they are vulnerable at high temperatures. However, aside from these minor complications, light-emitting diodes will surely be advantageous to you in the long run. Firstly, LEDs can fit easily into modern circuits and are fairly simple to install. They are incredibly efficient since there is no filament that must be warmed in order to produce visible light, and there is therefore no loss of energy through heat. This results in transferring almost all of the electrical energy into light energy. LEDs are much safer than other bulbs because they reduce the risk of combustion since they are much cooler than incandescent bulbs. Are you convinced yet? Well, if you're still skeptical, LEDs do not have a filament that will eventually burn out, and can therefore last much longer than the conventional incandescent bulb. LEDs are known to have a lifespan of more than 50,000 hours. LEDs are also much more durable than incandescent bulbs since they are made from epoxy lenses rather than glass. These types of lights produce uniform light dispersion, making them brighter than the incandescent bulb, and compared to the compact fluorescent bulb, LEDs contain no toxic mercury that can be potentially fatal to buyers. LEDs are easier and less costly to dispose of than CFLs because of the lack of toxic mercury present. Lastly, filters, as needed by other bulbs, are not needed by LEDs since they're built to produce light in a variety of colors. LEDs also have an impact on societal and environmental aspects, mostly in an advantageous way. For one, they are good for encouraging plant growth because the light intensity can be controlled and because there is no generation of harsh heat. Secondly, LEDs have the potential of relieving economic issues and reducing taxes within a community. A recent government study states that an LED put in effect for the next 20 years will contribute to saving approximately $250 billion in energy consumption. LEDs are responsible for the reduction of hundreds of pounds of CO2 per bulb, a significant figure when it comes to maintaining our environment. Lastly, LEDs lead to a safer environment because traffic lights that contain LED lights are more sharp and clear than a regular light bulb. LEDs are instant, which when put in a machine like a car's brake lights will lead to a safer environment. There are many implications of the LED in terms of its future development. Miscellaneous uses such as the LED high-definition television are well recognized for their superb quality and are sought out for by many. Most cars of today incorporate LEDs as part of their structure, for example, brake lights. Injection lasers are a new technology that uses a special form of LED, where there is a use of a flat junction. This injection laser emits electromagnetic waves and is used in clinical environments. Another future development of the LED is the LED light bulb, which is steadily being discovered and will soon be placed in our homes or workplaces. It's your turn now. Make a good investment and choose LED.
This is a photodiode. A photodiode is a type of photodetector capable of converting light into either current or voltage, depending upon the mode of operation. The common traditional solar cell used to generate electric solar power is a large area photodiode.
In this video, I'm going to talk about one of the most basic units of a solid-state image sensor, which is the photodiode. Photodiode. Well, what do I mean by photodiode? Here, I'm going to assume that you have some exposure to electrical engineering topics and say that a photodiode is really not much more than a diode. Let me draw the symbol for a diode. This is the common symbol for a diode. A downward-facing triangle, terminal, another terminal. And if I put a voltage across this diode, let's call it the diode voltage, the diode, I'm going to get an IV plot. Oh, sorry. Where this is voltage and this is current. This is V diode. The IV plot, let me draw the axes, it's going to look something like this. And then this current's going to shoot off almost to infinity. What you have are three distinct regions of the diode. You have here, where V diode is positive, you have forward bias, and here we have reverse bias. That's where we're going to operate our photodiode. And then you have this point here where V equals 0 and I equals 0. I forget the name for that, but that's what the deal is. Like I said, we're going to operate a diode, our photodiode, in reverse bias. And a diode is nothing different than a photodiode. Sometimes there's a little bit different structure in how they're built up, but for all intents and purposes, they're the same thing. Let me scroll down and draw the situation a little bit differently, how it's usually represented for photodiodes. So here, the diode was downward facing, but for photodiodes, it's usually drawn in the reverse orientation. We have something like this, okay? Or it's an upward facing triangle. What we have, that's a representation, the schematic, the symbol, for something that's actually going on within the semiconductor material. Okay, here's the semiconductor material that I'm drawing out here. And we have two regions. We have the p-type region, and we have the n-type region. I should make a note that in the discussion here, I'm mostly going to talk about visible image sensing, and the principles here are applicable to visible image sensing. Most of them are also applicable to infrared sensing. Photodiodes are the most common infrared sensor too, built in different kinds of materials like mercury cadmium telluride, gallium arsenide, indium gallium arsenide. But here I'm going to focus on silicon, and use it to detect visible light. That's what's going to dominate my discussion. This photodiode, this is the basic unit for photodetectors. Not all infrared detectors use a photodiode, but most do. So I'm going to discuss the photodiode. So here in this discussion I have n-type silicon on the top and p-type silicon on the bottom. What happens? Well, when you put this two types of material together, you're going to have some depletion width. There's going to be some depletion region that grows around this junction, and it's going to start here, say, and the width, this direction will depend on the doping profile. But now I'm going to reverse bias this diode. So usually what happens is you end up grounding this terminal, which means that to reverse bias it, this n-type terminal needs to go to some VDD. I'm going to say, in our case, plus 5 volts. So you can see that this plus 5 volts and this, I'll write it as plus 0 volts, results in a reverse bias diode, because the positive potential is applied to the n-type silicon, the negative potential, or the lesser potential, is applied to the p-type silicon. When you apply that potential, that depletion region will actually grow. And let's assume that the n-type silicon, the depletion region, has grown all the way to the surface of the silicon. And let's assume that for the p-type silicon. That's not all. That's in fact usually not the case by the way that photodiodes and image sensors are manufactured. But let's assume that we've fully depleted this volume of silicon. What happens when this volume of silicon is fully depleted and we illuminate it with visible light? So let's say we have a photon coming in with some energy, h nu. Well, if it has enough energy, it creates an electron-hole pair. What's going to happen to this electron-hole pair? Well, the hole is going to be attracted to the most negative potential in the system, and that's going to be 0 volts, so it's going to go there and just get sucked away to ground. The electron is going to be feel an electric field and try to go towards that plus 5 volts. That's what happens. We have a fully depleted volume of silicon. There's an electric field, and these charged particles will move according to that electric field. Now, we are going to collect electrons. For most image sensors, you collect electrons. You don't worry about holes. I have seen image sensors where you collect holes, but that's not the majority of them by far. Okay, let's talk about the electron. So the electron wants to go to that plus 5 volts. And the way I've drawn it here, it's a little misleading because in an actual, if you were going to instrument this photodiode as part of an image sensor, you wouldn't connect this terminal directly to a DC power supply because then that electron would zip away into the power supply and you would never see it. Rather, depending on the kind of image sensor you have, you'll either bring that electron out and store it on a capacitor, which will then create a voltage by Q equals CV, and then you'll read that voltage out through some sort of amplifier, or you'll store it in the pixel or jostle it around in the pixel by alternating clock phases, and that'll hopefully become a little more clear later on. But the basic idea is that this electron is going to be attracted towards the most positive potential in the system, and that's where we're going to read, and we're going to read that electron out as signal somehow. Okay, now as I mentioned, this is silicon, and we're talking about the wavelength of visible light h nu, or the energy of the visible light h nu, okay, where the speed of light equals the wavelength times the frequency, and you use this term to calculate the energy. What kinds of photons, what kind of electromagnetic radiation is silicon going to be sensitive to? Well, I scroll down.
This is a PIN diode. A PIN junction diode is made up of crystal of semiconductor. This is a Schottky diode, or the commonly known hot carrier diode, named after German physicist Walter H. Schottky. It's a semiconductor diode with a low forward voltage drop and a very fast switching action. And to know more about this kind of special purpose diode, check this out!
PIN diode is a diode that contains its own intrinsic semiconductor region between a p-type semiconductor and an n-type semiconductor region. PIN diode is a relatively good rectifier due to its wide I region. The feature of a PIN diode are most apparent in its operation on a high-level injection mode, when intrinsic I region is flooded with charge carriers from high concentration P and N regions that expose a direct voltage bias. Since the I region has a very low concentration of charge carriers, virtually no recombination processes take place there during the injection, but in the direct bias mode the charge carrier concentration exceeds the intrinsic concentration by several digits. At low frequencies a PIN diode is comparable to regular diode, and at high frequencies it performs as a virtually ideal resistor. Its voltage current characteristic remains linear even at very high voltages. At high frequencies, the I region contains a large volume of accumulated charge, which enables separation of the diode. At high frequency, charges in the I region are recombined and the diode powers off. In a PIN diode, the high frequency resistance is inversely proportional to the DC current flowing through it. Thus, the resistance can be varied in a very wide range, from 0.1 ohm to 10 kilo-ohm, by altering the direct current level. The wide I region also means that the PIN diode has low capacitance at reverse bias. Depending on their application, there exist mixture PIN diodes, detector PIN diodes, parametric PIN diodes, switch and limiting PIN diodes, semiconductor frequency multiplication, and tuned PIN diodes, oscillating diodes. PIN diodes are as a rule designed for operation in the centimeter wave range and uses attenuators, fast switchers, photosensors, and high voltage electronics.
Schottky diode.
The Schottky diode, also known as hot carrier diode, is a semiconductor diode with a low forward voltage drop and a very fast switching action. The cat's whisker detectors used in the early days of wireless and metal rectifiers used in early power applications can be considered primitive Schottky diodes. When current flows through a diode, there is a small voltage drop across the diode terminals. A normal silicon diode has a voltage drop between 0.6–1.7 volts, while a Schottky diode voltage drop is between approximately 0.15–0.45 volts. This lower voltage drop can provide higher switching speed and better system efficiency.
Construction.
A metal semiconductor junction is formed between a metal and a semiconductor, creating a Schottky barrier instead of a semiconductor. Semiconductor junction as in conventional diodes. Typical metals used are molybdenum, platinum, chromium or tungsten, and certain silicides, for example palladium silicide and platinum silicide. And the semiconductor would typically be N-type silicon. The metal side acts as the anode and N-type semiconductor acts as the cathode of the diode. This Schottky barrier results in both very fast switching and low forward voltage drop. The choice of the combination of the metal and semiconductor determines the forward voltage of the diode. Both N and P-type semiconductors show the Schottky effect. The P-type has typically much lower forward voltage. As the reverse leakage current increases dramatically with lowering the forward voltage, it cannot be too low. The usually employed range is about 0.5-0.7 V and P-type semiconductors are employed only rarely. Titanium silicide and other refractory silicides, which are able to withstand the temperatures needed for source drain annealing in CMOS processes, usually have too low forward voltage to be useful. Processes using these silicides therefore usually do not offer Schottky diodes. With increased doping level of the semiconductor, the width of the depletion region drops. Below a certain width the charge carriers can tunnel through the depletion region. At very high doping levels the junction does not behave as a rectifier anymore and becomes an ohmic contact. This can be used for simultaneous formation of ohmic contacts and diodes, as diodes form between the silicide and lightly doped N-type region and ohmic contacts form between the silicide and a heavily doped N or P-type region. Lightly doped P regions pose a problem as the resulting contact has too high resistance for a good ohmic contact and too low forward voltage and too high reverse leakage to be a good diode.
But wait, there's more. Let's watch these videos for other special types of diode.
Laser diode. A semiconductor laser used for signal transmission in fiber optics. The diode emits a high-powered light through a glass lens to minimize signal loss.
Today's discussion is on tunnel diodes. A tunnel diode is a semiconductor device, a diode, with a negative resistance region. It's the negative resistance region that allows for very fast switching speeds. Typical speeds can be in excess of 15 gigahertz. The operation of a tunnel diode is based in theory upon a quantum mechanics principle known as tunneling, wherein the intrinsic voltage barrier of 0.3 volts for germanium and 7 volts for silicon is surmounted with fabrication techniques that have been very heavily doped. In this demonstration, we're going to use a very fast switching tunnel diode, a 1N3713 tunnel diode, and compare it against the curves that are generated from a typical silicon diode. We'll be doing this on a curve tracer, and what we're particularly interested in looking at is the voltage versus current characteristics. For this demonstration, we're going to compare a standard diode that is not fast switching versus a tunnel diode that is extremely fast switching. On the left is the standard 1N4001 diode that can be purchased at American Micro Semiconductor. This diode will have conventional PN junction characteristics and were made with standard and conventional processing techniques. On the right side, we're going to look at a 1N3713 tunnel diode. Here the junction is made in a non-conventional method. Here what we're going to be doing is taking a look at a diode that is extremely heavily doped with impurities. Lots of metallization is put on the junction. If you look at the curve tracer and at the characteristics, here's what you're going to see. If you look here on the left-hand side, I have a standard 1N4001. I'll flip the switch so we can look at the forward voltage characteristics. Okay? Here you'll see conduction beginning to occur at about 0.5 of a volt. Now, let's switch over to the tunnel diode. Now, on the right-hand side, we are looking at the 1N3713 tunnel diode. I'll flip the switch. And now when we start forward with the characteristics, what you'll start noticing is that you'll start noticing here, this region in this area is referred to as your negative resistance area. It is in here that we do not see a curve, but that tunneling does occur. This is, in this range, is where you're going to be getting your quantum principles realized. Okay? In here, you'll notice that the curve almost goes vertical. Okay? There's a huge barrier that has got to be gotten over at this point. But if you look through here, you'll notice that there is no curve, largely due to the fact that we're working with a tunnel diode that is moving faster than the equipment can recognize the electrons or the signals from the processing. One other note is that in looking at a tunnel diode, we're talking about extremely low current values. If you look up here, we're actually looking at 200 microamps as being the maximum current that this is allowed to operate in. Typically, we want to be less than that. Okay? One of the other key characteristics of a tunnel diode is that when you're looking for your tunnel diode characteristics, you want to be looking at what might be referred to as your peak current. This is your peak current up here. Likewise, what we have is what we call is a valley current. So when you're specifying your tunnel diodes, you want to specify the range in which you want the tunneling concept to exist. Now, we'll switch back to the 1N4007, and you'll see that the total characteristics, what you'll see that the forward voltage drop is between 5 and 6/10 of a volt in your conventional diode. Okay? Now, this is a conventional diode. This is a diode with quantum principles involved. When you're thinking about high-frequency devices, consider American Micro Semiconductor as your solution. Also, you can buy these devices and shop at store.americanmicrosemiconductor.com for all your industrial, mechanical, military, and aerospace requirements. Thank you for watching our video, And stay tuned for the next in a series.
The topic for this lesson is varactor and other special diodes. The varactor diode operates in the reverse bias mode and is doped to maximize the capacitance inherent in the depletion region. When a PN junction is reverse biased, the depletion region at the junction has a width that is dependent upon the junction voltage. The depletion region is formed by accumulation of space charge. Because of this space charge and the voltage across the depletion region possesses properties similar to capacitance. The junction capacitance is inversely proportional to the width of the depletion region. If V sub j denotes the junction voltage and K is a constant, which is 0.333 or 0.5 depending upon the manner in which the PN junction is fabricated, then junction capacitance is proportional to V sub j to the power of K. Hence, the PN junction under reverse bias acts as a voltage-controlled capacitor. When a PN junction is used in this mode, it is called a varactor. The symbol for a varactor is shown in the illustration. The varactor tuning ratio is also called the capacitance ratio. It is the ratio of the diode capacitance at a minimum reverse voltage to the diode capacitance at a maximum reverse voltage. An important application of varactors is in tuning circuits. Varactors are used in TV tuners and other commercial receivers. The use of a varactor instead of or in addition to a capacitor in a tuned circuit gives rise to a voltage tunable resonant circuit. Such a circuit can be used in the generation of frequency modulated or FM signals. Pin diodes are another type of diode that are useful in high frequency circuits. They can switch at RF frequencies of more than 300 MHz. Beside RF switching applications, pin diodes are often used in modulation circuits. The specific frequency of a pin diode is equal to 1 over 2 pi times R, where R is the recombination lifetime of the device. The Shockley diode is constructed of two of each type of semiconductors in an alternating pattern. That is, if an ordinary diode can be designated as NP, the Shockley diode can be described as NP-NP. It is also known as the four-layer diode. Like other diodes, it has two terminals, an anode and a cathode. The Shockley diode is used primarily in switching applications. The switching properties are similar to a neon glow lamp. Each Shockley diode has an inherent trigger voltage. Below this voltage, the device is in the off state and has very high resistance. But on application of a voltage greater than the trigger voltage, the device will switch on and the resistance drops to a very low value. The on resistance for a Shockley diode is just a few ohms. If a third electrode called a gate is added to a four-layer Shockley device, the device is then known as a silicon-controlled rectifier, or SCR. When current passes through a substance, some of the electrical energy is converted into heat energy. The semiconductor device can be designed which converts this heat energy into light energy. This type of device is called a light-emitting diode, or LED. Like an ordinary diode, an LED will pass current in only one direction. When an LED is reverse biased, it simply blocks the flow of current like an ordinary diode. However, when an LED is forward biased, it glows or emits light energy. LEDs are used extensively in electronic circuits as indicator devices. Typical symbols for LEDs are illustrated. The laser diode emits light, but a much more powerful and focused type of light than an LED. A laser diode operates when it is forward biased. Most laser diodes can withstand only a relatively small reverse bias voltage.
Thank you for watching. Hope that you learned a lot about special purpose diodes. Till next time, goodbye!